So this is the last thing that we did. This is the last page we did, at least. I just want to talk about the top and remind us that mutually exclusive and independent are different. So we said mutually exclusive means that the events cannot happen at the same time. So if I were to give you two events in words, you can pretty much know whether or not they're mutually exclusive. Independent, though, we can't figure out just by taking a look. Like you saw in the warm-up, there's a way to test for independence. To know if events are independent, the probability of A given B should be equal to the probability of A, just for example. Today, what we are mostly going to focus on is independent event. Well, we're going to do conditional and independent. So this is where I need us to take a look. We're going to start out with an example. Shannon hits the snooze bar on her alarm clock on 60% of school days. If she doesn't hit the snooze bar, there is a 0.9 probability that she makes it to class on time. However, if she hits the snooze bar, there is only a 0.7 probability that she makes it to class on time. Part A, what we're doing is using a tree diagram. Before we do anything with a tree diagram, the very first thing you have to do is put things in probability notation and define events. There's only two things that are happening here. The first one is, does she hit snooze? So I'm going to let S be the event that Shannon hits snooze on her alarm clock. Besides that, the other thing it talks about is, does she make it to class on time? So that's going to be T. T is going to be, she makes it to class on time. So now we're going to put this in probability notation. So starting again, Shannon hits the snooze bar on her alarm clock on 60% of school days. So the probability that she hits snooze is 0.6. If she doesn't hit snooze, that's a conditional probability. So that is given she doesn't hit snooze. That's a complement. If she doesn't hit snooze, there is a 0.9 probability that she will make it to class on time. So that is the probability of being on time given she didn't hit snooze. So that's 0.9. Then it says, however, if she hits the snooze, so that is given she hits snooze, there is only a 0.7 probability she makes it to class on time. So making it on time is 0.7. So the entire tree is based on defining these two events and these probabilities. If you have the wrong notation, your whole tree is going to be messed up. We got a lot going on here. Okay, starting our tree. You good?
Is that your recording or is that outside?
The revving?
Yeah.
That would be outside.
Oh, I thought you were like, because you got, okay, never mind. Sorry.
No. Okay.
That'd be awesome if you did that.
Try it for next time. When we start out our tree, we're always going to start out with the single event. So in this case, we're starting out with, does she hit snooze? So there's only two possibilities. Either she hit snooze or she didn't hit snooze. That's it. Those are the only two probabilities, or the only two possibilities. Okay, the snooze probability we know. That's 0.6. So then that means 40% of the time she doesn't hit snooze. So these two have to add to 1. Okay, so next then, she hit snooze or she didn't hit snooze. After that, she's either on time to class or she's not on time. Those are the only two possibilities. So let's say that she did hit snooze. If she did hit snooze, again, there's only two possibilities. Either she's on time or she wasn't on time. But these are givens. Given she hit snooze. Given she hit snooze. So she hit snooze. So this is now she's on time given she hit snooze. Or she's late given she hit snooze. Now we know one of them, T given S. So that is 0.7. If we already know she hit snooze, 70% of the time she's on time. So the rest of the time then, she's late. So that one is 0.3. So So then down here, it's going to be the same idea. If she doesn't hit snooze, again, she can be on time or she's not on time. So this would be she's given on time or she's on time given she didn't hit snooze. Or she's late given she didn't hit snooze. And again, we should know one of those. We know that 90% of the time she's going to be on time given she didn't hit snooze. Which means the remaining 10% of the time when she didn't hit snooze, she's going to be late. So this is the tree diagram. This is going to help us answer the following questions. We okay so far? Okay, we're going to add to our tree, but we're going to leave it right there. So again, what I want to point out, these two add to 1, these two add to 1, these two add to 1. So B, on a randomly chosen day, what is the probability that Shannon is late for class? So we are looking for what is the probability that she is late, that she is not on time. Now, looking at all of the information that we have, we don't really have anything at this point that's helpful. So we have to think, how would this occur? So if Shannon's late to class, how does that occur? Well, there's only two possibilities. Either she hit snooze and she was late, or she didn't hit snooze and she was late. So she hit snooze and she was late, or she didn't hit snooze and she was late. Do we agree? That's the only two ways that she could be late? So really what we need to find is these two probabilities, and we're going to add them together. That comes from the tree. So what we're going to add on now to our tree off of each of these branches, you're going to add a horizontal. Now what happens, similar to what we saw in the warm-up, when we multiply these two probabilities, we get an and. So this first one is the probability of T and S. And if we want to know why, well, the probability of T given S is the probability of T and S over the probability of S. So T given S, I just took that from the tree. So T given S, this is now a formula that's on the formula sheet. So if I put this over 1 then and multiply, I see that the probability of T and S is the probability of T given S times the probability of S. Well, these two are just the previous two branches. T given S is right here, S is given here. So when I multiply the previous two branches, I get an and. So that tells me then, the next down, this is going to be the probability of T complement and S. Then I'll have the probability of T and S complement. And finally, the probability of T complement and S complement. So all I'm doing is when I multiply these two, the conditional turns into an and. Conditional turns into an and. So then I actually multiply. So my 0.6 and 0.7, so that top probability is going to be 0.42. Then I do 0.6 and 0.3, and I get 0.18. 0.4 and 0.9 gives me 0.36. And 0.4 and 0.1 gives me 0.04. So all of those green probabilities are going to sum to 1. So this is our full tree. So now when we want S and T complement and S complement and T complement, those just come directly from the tree. So S and T complement. S and T complement. That's this one right here. And then T complement and S complement is right here. So then we say, okay, I'm adding up the 0.18 and the 0.04. So my probability of T complement then is 0.22. So what does this tell us? 22% of the time, Shannon is late to class. We okay before we do part C? So part C. Suppose that Shannon is late for school. What is the probability that she hit the snooze bar this morning? Okay, so suppose she's late for school. So given she's late for school, what is the probability that she hit snooze? Well, this is now just a formula. We did it in red. It's a formula right off of the formula sheet. This is going to be the probability of S and T complement over the probability of T complement. Well, S and T complement, that's on the tree. So S and T complement, that's right here, 0.18. T complement, we just calculated above, was 0.22. And if you divide those, I'm going to tell you it ends up being about 0.82. So what this is telling us, if she's late for school, she probably hit snooze. So given that she's late for school, 82% of the time that she's late, she did hit snooze. Okay, we got 2 more things to write down and then we'll take a break. Questions for me? Okay, general multiplication rule. I'm not going to show you the rule, we're going to find it. General multiplication rule is not on your formula sheet. On the formula sheet, though, we do have the conditional probability. So the probability of A given B is equal to the probability of A and B over B. Right, so that is your conditional. That's just on the formula sheet. So all that the multiplication rule does is it takes that formula and it solves for A and B. So A and B is the probability of A given B times the probability of B. That is not something that you need to memorize. All you're doing is going off of the formula that you are given on the formula sheet. Okay, and then lastly, we need to know when to use this tree diagram. So in the notes here, I told you, use a tree diagram. I'm not going to in the future. In the future, you need to read from the question and know to use a tree. So when do you need to use a tree? When events are sequential. I'm going to say and or, really not, it's really and conditional. So when events are sequential and they're definitely. Now that you've seen this tree idea, of course, you're going to have to do one yourself. So that's what we're doing next. This next question, before we read it, I'm going to tell you, I'm going to get you started because if you define your events wrong, everything else is going to be wrong. Many employers require prospective employees to take a drug test. A positive result on this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs, the false positive rate is 5%, and the false negative rate is 10%. Okay, so a lot of us, I think, are okay on the first event. The first event, I'm going to use D to represent a drug user. What is the second event? I think that's what a lot of us want to do. False positive, false negative. It's not that, though, unfortunately. What's the other thing that it talks about here? Evan?
Maybe like test result.
The test results, yeah. Specifically testing positive. So T is going to be test positive. So like the last question that we did, you're going to have to come up with 3 probabilities before you draw your tree. So what you're going to do is work with the person next to you, come up with all 3 probabilities, draw the tree, and then you should be able to answer A or B. If you're unsure on your probabilities, ask me, because if you have the wrong probabilities, the whole tree is going to be messed up. Good luck. Okay, the first one, it says blah, 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 4% use drugs. So it should be the probability of using drugs is 0.04. False positive. A false positive would be we got a positive result and it was wrong. If we got a positive result, what is the correct event that is matched with that?
No, they're not a drug user.
If we got a positive result, they are a drug user. So if it's a false positive, we took non-drug users. So we gave a test to a non-drug user, and we still got a positive result 5% of the time. And then false negative means we got a negative. If it's false, it came from a drug user then, which is 0.1. Those have to be conditional. They are not the same as ands. And a lot of us wrote it the other way, which is also not true. In this case, what we know or don't know is whether the person uses drugs, and then we care about what is their test result. Okay, thank you for letting me interrupt you. Please finish the rest of your tree in A and B. Call me over when you get the answer to A, please. Okay, so if you look up here, my tree is in blue. Some things that I want to point out to you. What I should have done before, it's not a huge deal, but really it should be P here for all of these, for probability. So really I should be having P. If you don't, that's fine. The biggest deal to me when I walk around is these probabilities. These are conditional. If you just write P of T complement, that's wrong. This is a conditional probability, all of those in red. You need a fully labeled tree because that is your work. So then in part A, testing positive, that happens only two ways. Either the person tests positive and they use drugs, or they test positive and they don't use drugs. So that is 0.084. And then in B though, what percent of prospective employees who test positive? So given test positive, what's the probability of using drugs? Oh, what did I do wrong though in my answers? Yeah, it did. It asked for a percent, and I did not give a percent, so I'm glad most of you did. So we get 42.9%. Did you guys take a look at that answer in B? Like in context? What does that answer in B mean in context of our two variables? Evan?
It means you're more likely than not to test positive if you don't use drugs. Like more people who don't use drugs will test positive than people who do.
Right. Did you guys notice this? If we look at everybody that tested positive, only 43% of them actually use drugs. That seems like a really low number, right? Okay, that's the correct answer, but that's what it is. Have any of you ever had to take a drug test for work before? Yeah? A lot of times if you take a drug test and you test positive, the very first thing they're going to do, test you again. Test you again.